Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on software MBAL. All right, and today's video is about well by well history matching. Okay, so we are now inside the MBAL. You can follow me. We go to this one tool, material balance. All right, and then we can open the options, reservoir fluid, oil, tank model, single tank, PVT model, simple PVT. Production history now is important. We change from by tank to by well. Okay, and then for the compositional model, none. Okay, you can type in the user information like company, field, location, platform, analyst, and also the user comments here. All right, click done. Okay, so from here, we can input the PVT, go to fluid properties. All right, you can follow me. Formation GOR 500, standard cubic feet per stock tank barrel, oil gravity 39, gas gravity 0.8, water salinity 100,000 ppm, no H2S, no CO2, and no nitrogen. If you have laboratory data, you can use this match and you can perform PVT matching, but we will skip PVT matching for the time being. All right, click done. Okay. All right, so from here, we go to input and we select wells data. All right, and now we will create the first well. Press this one. Okay, so now we have well one setup, well type oil producer. You can open the drop down menu. Okay, and we select oil producer for the well one, production history or production allocation, relative permeability. Okay, go to production history and you can see now we have the table, and in this table we can input the production history of this well. All right, so previously we learned about MBAL using tank production history data. In this particular video, the production history comes from each well. All right, so I need to prepare production history from well one and from other wells also. All right, so let me prepare, let me copy the production history and then paste the data here. All right. Okay, so I've copied my data from my spreadsheet and then pasted the data here. I have the production history starting from 1997, the January, through 2002. All right, December 2002. Okay, and then I can plot the production history, plot. All right, this is the cumulative oil production of well one. Okay, I can remove all. Reservoir pressure. You can see I don't have reservoir pressure history. This is the cumulative oil production. Remove all. This is the cumulative water production, cumulative gas production. Okay, so far so good. You can see I have the data for time, cumulative oil produced, cumulative gas produced, cumulative water produced, and I don't have any pressure data for this well one. All right, and from here, we can go to the next step, production allocation, this one. All right, and I need to input the fraction, okay, or percentage. In this case, I prefer fraction. So what do I mean by this is that the production from well one, all right, starting from this date, January 1997, the fraction is 1, okay? So that the all production from well one will be contributive to the tank history or the production history of this reservoir. 100% of the production of well 1 will contribute to the production history of the overall reservoir. All right, so far so good. Okay, I don't need to input relative permeability data in this step. So you can validate and done. Okay, and I can also input the tank data. If you have the data already, you can input the data now. Okay, but let's say I will prefer adding new well. So I will click this one again. I create well 2. Okay, so now I have 2 wells. If I press done, I have 2 wells. I will move the second well there. All right. Okay, now double click at well 2. Still, this one is oil production also. Oil production well. Production history. I will copy the production history for this well from my spreadsheet and then paste the data here. Okay. All right. Right click, paste table. Okay, so this is the prepared data, the production history data for the second well, for well 2. All right. This well produced from 1999, and we have the production history through, again, December 2002. All right. And again, you can plot. I have the cumulative oil production data for the second well, and I don't have reservoir pressure for this well also. Okay. I can remove all. I can show you the cumulative gas production, cumulative GOR, okay, and cumulative water production. So far so good. And from here, we can go to the production allocation. Next. Okay, so again, the production of this well, the total production of this well will be contributive to the production history of the tank or of the reservoir. So that's why I put fraction of 1 for this well, starting from January 1999. Okay, so it means that 100% production from well 2 will be allocated to the reservoir. So it means that the production from well 2 doesn't go to the other reservoir or another reservoir. 100% production from this well will go to this reservoir, this tank. Okay, so far so good. Validate. Next. Again, we don't need to input relative permeability data at this step. Okay, click done. Okay, so now I have prepared 2 data or 2 wells, well 1 and well 2. And now I need to input data into the tank 1. Okay, you can follow me. I have prepared my data for tank 1. Temperature 250 degrees Fahrenheit. Initial reservoir pressure 6,000. Porosity in fraction 0.23. Water saturation 0.15. Water compressibility will be calculated using correlation. Gas cap, no gas cap. Original oil in place in MMSTB 217. Start of production, of course, as per the first well, the well 1, it is on 1st January of 1997. Okay, water influx, let's assume it doesn't have water influx first. Rock compressibility will be calculated using correlation. No rock compaction and relative permeability data we can input. All right. relative permeability from Corey functions, hysteresis no, modified no. And then for this table, you can follow me. The endpoint 0.6, exponent 1, to make it simpler, 0.8, 1, 0.02, 0.9, 1. Okay, well allocation, well production allocation, 100% from well 1, and 1 from well 2, 100% from well 2. And now we go to production history tab. All right, so from here, we can press calc, okay? And let's read the remarks here. Warning, limitation of method. To calculate an average pressure, a detailed description of the geology is required, okay? However, if we assume an isotropic reservoir and all wells start and stop at the same time, we can estimate a drainage volume proportional to the rate. All right, so this is the condition. We have isotropic reservoir and all wells start and stop at the same time. Okay, if the assumptions are in any way invalid, then the calculation will yield incorrect answers. In this case, the calculation of average pressure must be done outside of MBAL. Okay, and you can see that the well 1 and well 2 don't start and stop at the same time, and that's why we cannot press calc to obtain the average reservoir pressure. That will give us error, that will give us incorrect reservoir pressure. So in this case, let's say I have another well, monitoring well, from which I can obtain reservoir pressure data. All right, so that will be our game plan. Okay, so I prefer pressing calc first. Okay, and then the reservoir pressure obtained from the MBAL from the calculation will be erased and changed with the prepared reservoir data obtained from monitoring well. Okay, so let's press calc. The calculation is complete. All right, interesting, right? So we have time, we have cumulative oil produced, we have cumulative gas produced, cumulative water produced, no cumulative gas injected, no cumulative water injected. But now you can see we get reservoir pressure data from the calculation, and you know that we cannot use this reservoir pressure result. You can see it's not right. The reservoir pressure is 6,000 all the way through the years from the start of the production till the end of the history. And we will change this reservoir pressure data with our data. Okay, so I will copy the reservoir pressure data and paste the data here. All right, I've copied my data, and then I will right click here, paste table. All right, I need to be careful. Calc. Okay, so we need a strategy here. I need to input the pressure data here, but I cannot just paste table. All right, that will erase all the columns, all the tabs, all the cells. So let me try another strategy. So instead, I will copy this entire table. Okay, I will copy this entire table. I will paste this table to my spreadsheet, and then I will change the data at this column at my spreadsheet with the correct pressure data, and then I will copy the table on my spreadsheet and paste the table here. All right, so you can do that on your spreadsheet. I will just do that in my spreadsheet and then paste it here. Okay, so I right click, copy table, All right, I will clear the table and then right click paste table. Okay, so this is my data. You can see now I have correct reservoir pressure data obtained from the monitoring well. All right, I have the entire production history combined from the production history of well 1 and well 2. All right, I can plot. Okay, so this is the plot. I have reservoir pressure data. Interesting. And I have the cumulative oil production data. You can see here we have a significant drop of reservoir pressure. Okay. And also we have significant rise of cumulative oil production. Okay. Here. Why? Yeah, because we have a new well, well 2. Okay, so the history of this pressure decline is caused by the production from well 1, and at the January 1999 we have another well, which is the well 2, and it caused the reservoir pressure to drop significantly. All right, but again it will decline and follow a pseudo steady state regime later on. Okay, and you can see the slope changes at this point because of contribution from a new well, the well 2. Okay, remove all. You can also plot the cumulative oil production with cumulative gas production, the same trend. Remove all, cumulative water production, cumulative GOR. Okay, so far so good. So now we've prepared the table. We have this production history table from the reservoir and also from each well. Okay, so as usual, we click done, and you can see we have well 1, tank 1, and well 2. And as usual, we will do history matching for this case. Okay, you can open the history matching tab. All right, you can see we will do analytical method, graphical method, and we will see the energy plot, and we will run simulation, and we will also do this one. Okay, the matching for the fractional flow. Okay, so let's go ahead. Let's try analytical method first. You can see this is the pressure data, and this is the pressure results, assuming no aquifer. Clearly, you can see it doesn't match. So the first thing that I will do is to put or to create an aquifer for this model. Okay, so let's click finish, double click, and go to water influx tab. All right, I will make an aquifer, and I will choose this model, Hearst Van Everdingen modified method. I will assume radial aquifer, reservoir thickness 250. Let's say I already analyze this aquifer and I input the results or the information for this aquifer into this step. And later on, I will again do the history matching. Reservoir radius 2500 with ratio of 6. Encroachment angle 250 with aquifer permeability of 7. Done. Okay, so now we have water influx, we have aquifer, history matching, analytical method. That's better, right? You can see this is the data, and the results with aquifer influx is shown by this blue line, whereas for the results without aquifer influx is shown by this red line. Okay, to obtain a more perfect matching, I can do regression. Okay, and I will, let's say, adjust oil in place, radius, I already know the reservoir radius, so I will not check this one. I will also regress the encroachment angle. I'm quite satisfied with the reservoir thickness, so I will put it. Aquifer permeability already good. Aquifer permeability, I will regress. Okay, and let's say for this one, I will put it at these numbers, and then this one 7. Encroachment angle 250 with 300. Aquifer permeability from 5 to 7. Okay, let's calc. All right, so the regression has been completed, and this is the numbers: oil in place, outer inner radius, encroachment angle, aquifer permeability. So no significant change actually from the original input. So let's check it out. Use this one. Okay, done. All right. So we have achieved, if I say it, a perfect match. Okay. So now let's say we can trust these results: the new oil in place, the new outer inner radius, encroachment angle, and aquifer permeability, with the other parameters kept being constant. Click done. Okay, so now we have done the history matching. Finish. Let's check the graphical method. Okay, the first method already quite good, and this is the results. All right, quite close with the analytical method results. Let's check another method, Havlena Ode. Very good. And this is the oil in place calculated from Havlena Ode. So I'm satisfied with this. Another method, very good. This is the result. And then, all right, Campbell method, good. Also good. Okay. So the results from graphical methods differ very slightly. So I'm confident right now that the oil in place is close to 218 million stock tank barrel of oil. Okay. All right. This one is also good. Lastly, do you wish to save? Oh, I prefer not. Okay. So this one from this last method, assuming no aquifer. So I will not prefer this method to assess the result, right? Okay, so I'm quite satisfied with the matching results from graphical method. Okay, let's check the energy plot. All right, interesting. So you can see that the dominant drive mechanism for this reservoir is water influx. We also have fluid expansion and pore volume compressibility. All right, that's natural, that's automatic. All reservoirs will have fluid expansion and pore volume compressibility contributions. But in this case, we also have water influx as the dominant drive mechanism. Okay. And we can also say that the aquifer model and the aquifer parameters are already reliable. Click finish, history matching, show all. All right. The analytical method, the drive mechanism or energy plot, and also the graphical method. And here we have this one already match also. This one is actually this one. Okay. The flow rate versus the dimensionless time. It shows the quality, the good quality of the matching we have achieved. Okay. Click done, history matching. And now I will also do run simulation, calculate, completed, very fast. And I will plot history. I will show the tank pressure. This is the tank pressure from history. This is data and the simulation, tank pressure. The red line is the result, whereas the black dots are the data. So you can see we have achieved perfect match between the real data and the simulation. Okay, and then remove all history. I have data for cumulative oil production, and I will show the cumulative oil production from simulation. Okay, which one? This one? Perfect match. Okay, but now due to the simulation, I can show you the oil flow rate. I don't have the data for oil flow rate from the data, from the well results or well data. Okay, I only prepare cumulative oil production data, not the oil flow rate. But from simulation, I can extract the oil flow rate. And that's why I want to show you the results. Average oil rate, this one, this is the production from well 1, and this is the production from well 1 and well 2. What about the gas rate? The same trend. Water rate, okay. And also recovery factor. This one is also very important. You can see up to 2002, we still achieve 21%, the recovery factor. Quite good, but I think we can increase the recovery factor, for example, by continuing the production or by adding another infill well, right? What about the oil saturation? You can see the oil saturation drops due to production, of course, from 85% to 68%, which is still quite high. So you can see by continuing the production or by adding another well, we can increase the recovery and we can decrease the saturation further. And also you can check the aquifer influx. Of course, this influx is calculated using the method that we selected, the Hurst and Van Everdingen modified method. You can also get the reservoir voidage, right? No injection, reservoir voidage balance, and others. All right, so very, very interesting. Okay, so we have completed the data preparation. So we also combine the production from well 1 and well 2 and combine them into the reservoir. And also I add up reservoir pressure data from monitoring well. And I've done the history matching, analytical method, graphical method. I show you the energy plot. And now we will do this one. All right, the fractional flow matching. And after that, we will do production prediction. So let's go ahead. All right, so let's go to the history matching tab and go to FW matching. So FW is the fractional flow for water, and we will do matching here. This is the FW matching for the tank. Because we want to do prediction, we need to perform matching for well level. So click this one, well. We have well 1 and well 2. First, we go to well 1. Okay, so this is the fractional flow constructed from the historical data. This one, these data points. And before going to the prediction, we need to match these data points with this blue line. Okay. And we can easily do that by pressing this one, regress. Regress on default variables. All right. Okay, so we have completed the matching. So now the data points and the simulation are matched. And we need to do that also for well 2. Save regression results in well relative permeability parameters. Yes. This is the condition for well 2. Regress. Okay. So now we have completed the matching, the fractional flow for well 1 and well 2. And we can do prediction starting from now. Okay. Yes, save regression results in well relative permeability parameters. Okay. It's okay for the tank. For well 1 already matched, well 2 already matched. Finish. Open well 1. You can see now we have relative permeability parameters inputted, residual saturation, endpoint, and the exponent. You can check the plot. A value must be entered. Here, doesn't matter because we are done in this section. Okay. All right. Yeah, if you want to show the plot, you can also input the data for gas breakthrough in this section. Okay, but we can skip it for the time being. All right. So we have completed the history matching, the analytical method, right? We complete the matching by adding water influx to the reservoir model. And we also achieve very good matching for graphical methods. We generate the energy plot showing that the water influx or water drive is the dominant drive mechanism for our reservoir. And we also perform matching for well level, the fractional flow matching. And now we are ready to do prediction. So let's go to production prediction, prediction setup. Okay, so from here, for the predict, we can open the drop-down menu. And in this case, we will choose production profile from or production profile using well models. And for the options, we check the use fractional flow model. Okay, and then for the prediction step size, automatic. And for the prediction end, in this case, we will end the prediction at 1st January 2015. Okay, for prediction start, we will start the prediction from the end of production history. All right, so we have production history, and of course, we will start the prediction. I recommend you to start the prediction at the end of production history, and you can end the prediction at this date or at your preference date. Okay, so we can click done. All right. And now again, production prediction, this one, well type definition. Okay, you see here we have two history wells, history from well 1 and from well 2. Okay, to the prediction, we will create a prediction well, which is actually the same well. So well 1, this is for history well, but now I will create a prediction well version for well 1 and prediction well version for well 2. Okay, so click this one, well 1. Okay, if I click done, I have this new well, which is actually this well, but used for prediction. Okay, that's what we do in MBAL software. Okay, so I will move this first. Okay, and also I can also add second well. Click done. Move the second well for prediction well. All right. Okay, so we can go to the first well. All right, you can see we have set up well type oil producer. Okay, and we have inflow performance, more inflow, outflow performance. Okay, let's be careful here. We start with inflow performance. And for inflow performance model, we will use straight line productivity index plus Vogel below the bubble point pressure. Okay. And fractional flow model, we will use this one, use rel_perm1. Okay, but we need to edit the data. Okay. All right. Here we have rel_perm from Cori function. Okay. And then hysteresis no, modified no. And here we can copy the relative permeability results obtained from the previous fractional flow matching. Okay, so click copy and you select this one, material balance from well 1. Click copy. Now I extract the relative permeability results from fractional flow matching for well 1. I extract that and distribute the data, the results to this table. Okay, residual saturation, the endpoint, and also the exponent. All right, so far so good. Done. Do you wish to copy the water breakthrough from the copied relative permeability curve? The water saturation at 15%, yes. Okay, and here we have productivity index. I will input 15 stock tank barrel per day per PSI. Test water cut 0. All right, and the other, let's leave it as per default. Okay, done. Inflow performance for well 1. And we do that for the second well. Or I can prefer using rel_perm 2, copy from well 2. Okay, and I will put the productivity index to be 10 stock tank barrel per day per PSI. Validate. All right. Now go back to well 1, check more inflow. Let's leave the other or leave this step as per default. And now we go to outflow performance. All right. So from here, we have outflow performance selection, either using constant flowing bottom hole pressure or tubing performance curves. Okay. And in this case, I've prepared the tubing performance curves. I've prepared the VLP, the vertical lift performance, and I will put the results, the prepared VLP or the prepared TPC to MBAL. I click edit. All right. And now I will import. Okay. I just prepare the data and I will press import. Okay. All right. And from here, I will select this one, open. Okay. Finish. All right. So automatically populated the VLP data. All right. This one, in my opinion, is the most troublesome, the most complex section of the MBAL, but you can easily create this data using well modeling software like Prosper. You create several scenarios for wellhead pressure, or in this case, manifold pressure, water cut, GOR, and you will extract this one, the flowing bottom hole pressure from the scenarios. And I can plot. This is the plot. I have the IPR and I have the VLPs. All right, finish, done. Okay, done for first well, or I now will complete the well 2, edit, import this one, done, plot. All right, finish, finish, done. Okay, so I've created 2 prediction wells, which are actually well 1 and well 2. Okay, but Here I have history well 1, history well 2, and now I create prediction well 1 and prediction well 2. Okay, so we go back to the production prediction well schedule. Okay, I will make the start time from the end of history, which is 31st, okay, December 2002 for both wells. Copy and paste, and I will end the prediction at 1st January 2015 for both wells. Okay, number of wells 1 and 1. This one for prediction well 1 and this one for prediction well 2. Downtime 0. No shut in, no downtime. Okay, click done. Okay, we are almost there. Reporting schedule, automatic. All right. Okay, now for production constraints, we check. Okay, for the production or the prediction, production, and constraints, I've prepared the condition. I copy the data and paste it here. Paste table. Okay, let me do this manually. All right, starting from the 31st December of 2002, the manifold pressure or wellhead pressure is 1000 psig. Click done. Go back to production prediction. Now I can do run prediction, calculate. So you can see I start the prediction from this date, 31st December of 2002. And now I have the results for tank pressure, oil recovery, oil rate, gas rate, water rate, liquid rate, the average oil rates or the average rates for oil, gas, water, and liquid, and the other results, including voidage balance, reservoir voidage, downhole pore volume, and others, including also aquifer influx, of course. So if we go to the end of the table, the final oil recovery factor at 1st January 2015 is 36%. Okay, let's make the plot. Start from history, tank pressure, also show the simulation results for tank pressure. And what about the prediction? Tank pressure. Okay, so this is the profile for the forecasted tank pressure. You can see we get increased pressure here. Maybe this is because of the water influx. Okay, and after that the pressure declines again. Remove all. I want to show the history. Oil recovery factor is not in history, but I can show the simulation, the oil recovery factor from simulation. This one, you see at the at the end of the production history, the final oil recovery factor is 21%. And I do the prediction, I do the forecasting, and I will show the recovery factor, this one. Okay, so now at 1st January of 2015, I can achieve oil recovery factor of 36%. I can also show the oil flow rate, this one, production from well 1, production from both well 1 and well 2. And what about the prediction, oil rate? Okay, so this is the forecasted oil rates from well 1 and well 2. Okay. Yeah, you can also show the other results. Remove all, like water influx or aquifer influx, prediction, aquifer influx. Okay. And I will overlay with tank pressure and also for the prediction. Okay. So as you can see here, the pressure drops significantly because of new contribution from well 2, and the aquifer influx increased at that time. Okay, due to this one, due to the decreased pressure at reservoir side, it will increase the driving force so that the aquifer influx increase at that time. All right, so this this is the thing that you can do using this case. Okay, so you perform combination of well 1 and well 2 to get the overall production history, and then you add also with information regarding the reservoir pressure obtained from your monitoring well, and then you perform history matching for reservoir level, and also you do fractional flow matching for well level, well 1 and well 2, and then you input the VLP, input the IPR, okay, you input the nodal analysis, and you also create the, or you also input the production constraint, production scheduling, and yeah, you just do the prediction, the forecasting, and this is the results you will get. Okay, so it's very easy, right? All right, so I think we can call it a day. Okay, this is the final results that we get. Okay, so that's all. I hope this video is useful. I hope this video will stimulate you to study further using this MBAL software, which is very, very useful. And see you again in the next MBAL videos. Thank you.